Everyone, we are starting our last chapter. Wow, we're already at the last chapter, and there are two sections to cover. You can see them here: 16.1 vector fields and 16.2 line integrals. 16.1, I hope you'll agree with me when we're finished. It's pretty easy. Certainly a lot simpler than a lot of the things you've had to tackle in the last few weeks, so that's good. Quite a lot of this is going to be just using software, where you're going to graph what's called a vector field, and there'll be like 4 pictures and you pick the one that looks like it. So that makes this homework very fast as well. And then at the tail end, we'll create a particular kind, a very popular vector field, and it's a guy you already know. It's a gradient. Actually, the gradient's full title is a gradient field. So that'll be the last few questions, and 16.1 should probably take us, I don't know, half an hour. And then we move on to the kind of bread and butter stuff, which are line integrals. Now, not being an engineer or even wanting to ever become an engineer, evidently line integrals are things that they're interested in. And when we get to that, I'll talk a little bit about what a line integral is. And there are different versions of it. As you can see, there are 3 specifically different flavors of a line integral. The last one is one I know most about, which is basically it's a line going through 3D space, passing through a vector field, and you're trying to calculate the work done. All right, so how much energy, or whatever you want to call it, it would take to take a particular pathway through a vector field. And you can think of a vector field, an analogy might be, can you imagine in the air, you've got wind currents, and sometimes they're blowing one way and sometimes, they're blowing up the way and down the way. So a vector field would basically be a way to represent a 3D space, where every point in that 3D space, there is a vector indicating, in this case, the direction that the wind and the force of it in any given point. And so that one's, to me, the easiest to visualize. I can't really visualize what these two do. They are line integrals, and maybe someday in engineering will one day say, yeah, we need this guy or that guy, but I can't give you any practical examples of it. And this one here, I can see that being applicable pretty easily. So let's start you off with what a vector field is before we do the software. A vector field is typically written like that, and it's given as a vector. So an example of a vector field could simply be this. Oops. So can you imagine at any point in XY space, there's a vector that you get by this function. So let's suppose that point there, let's call it P. And let's say I had coordinates 1, 2. So that would mean its X coordinate is 1 and its Y is 2. Then the vector that you would associate with that point in space would be 2 times 1 is 2, 2 times 1 plus Y, which is 4. And so you can imagine here, you'd get a vector that would be 2 along, 4 up. You make a vector like that. Now, can you imagine taking lots and lots of points in XY space, and for every single one of them, you used this formula to calculate what the vector would look at any given point? Now, I'm not even going to attempt that this is accurate, but can you imagine you might get a vector field like this? Now, since you can't do an infinite number of points, what you tend to do is you tend to just do, 1, 2, 3, 4, 5, 6, right? Just little snapshots of the whole thing. So can you imagine we might have got a vector field that looked like this guy? So almost like a wind pattern. Can you see at different points in space the wind is blowing differently? If the vector is a short vector, it means the length of it is small, and therefore you're going in that direction, but the wind's not blowing particularly hard. If you go in another one, it might be blowing really hard. So that's essentially what a vector field does. Any point in 2D space has a vector associated to it using whatever formula that you give here. So what we're going to do is some questions involving drawing vector fields. Right, so right now you should be looking at Desmos, not Desmos, Canvas. You're looking at Canvas, and do you see this guy here, vector field in 2D? If I click on that, hopefully it's set up, at least I put it up there, it should be working. Here we go. Now, there's the vector field that this one is doing. You see, oh, that's quite pretty. You see that? Right, and it's generated by the x component of the vector is this guy, and the y component is that guy. And he's not calling these guys, I don't know what he's calling them. He's calling them these guys. I'm just going to call them, I would call this guy P. That's what I typically do in my notes. And I'll call this guy Q. So let's do a vector field where the x component is made up of x plus y squared. And the y component is made up of 2xy. And there's my vector field. Now, and this is two-dimensional, but if you look at this vector field, if you start at the origin, isn't the vectors are either pointing in or away from it, and the further away you get, can you see on this side, it's going this way, and in this side, it's heading towards the middle, but getting weaker, right? There's some kind of structure to that, and that's what a 2D vector field looks like. So far, so good. So let me find a homework question where I can do that. And not that one. We find. Okay, where are you hiding? There you go. In question 1, the vector field that they gave you is y goes there, and x plus y goes there. And when I click out of that one, now if you can't see much, you are allowed to move some things around. So I can, for instance, make the vectors longer just by adjusting this scale. That's probably good enough. Right, do you see that pattern? I mean, it's a lot going on. Then what you then would be doing in your homework, and I wish I had like split screen or something, you could probably see better what the heck's going on, but I don't, so you can't. Here, this is the choices that we've got. Now, I've still got the guy in front of me, so my life's a little bit easier than you. But if you look at the patterns that are going on, the guy that looks most like the one I've got is this one. And that would be my picture. And that's the end of the question. So let me return back to my notes. And you're going to get a number of questions that are basically, here is a vector field, sketch it and pick whoever the guy is from the two choices. Okay, I'm going to have to close some windows off here because I just can't handle 10 windows at once. My brain's just not good enough. Okay, now I gotcha. Right. So for instance, in question 1, the vector field f, you can think of it as a function of x and y, was given by y, x plus y. That was the one I just did, and I believe it was picture 1. They can also give you a vector written in that format. I don't like that format, but it's the same as I get. Now, if I zoom on to question 2, the guy that we're going to draw has an equation, a formula that looks like this. yi plus xj over the square root of x squared plus y squared. That format does not work with my brain. I like to separate them out like this. Okay, let's see that. The I is the X component, the J is the Y component. If you forget about this guy, can you see the Y over X squared guy? And if you forget about this one, can you see the X? So that's what the guy would look like. Now, if you plug that into the 2D guy that I got, you will be able to see which of the choices of 4, right, match this picture, right? So here I go and jump through 5 hoops to get the right window. And who do I have? Okay. I should be able to do that guy. The first component, that's basically the X guy, is going to be equal to Y over the square root. So let's see if I can do it in this one. Sometimes you have to get the format right. Y divided by, will it take the square root? Or will I have to hit this little keyboard? Let's see. Hello keyboard, okay. Square root. Well, I'm there. Let's try that again. Y divided by. I'll try to get the format here, and should have spent some time practicing with this guy. X squared plus Y squared. Right. No. There we go. And the other one is basically going to be that guy. Oh, it's got dotted lines around it. And third attempt. Okay, work I tell you. Yay, okay, gotta work. Just took a little while to figure it out. Y divided by essentially the same guys. I'm going to have to use the little keyboard. That seems to be the way it works. Although looking at it, it should be able to handle X square root, but evidently when I typed it, it didn't. Boom. Okay, why is it not like that guy? Oh, because I can't do brackets. I need a new set of eyes. Third time lucky. Okay, can't see much there. Why don't I move this guy a little bit? Move this guy a little bit. There we go. There. In this picture, can you see the center is like exploding outwards? Right? From the origin, every vector seems to be going in an outwards direction. So what I would then have to do is pick one of my pictures that looks like that and call it good. I really do need a split screen. That ain't going to happen. Now I'm going to zoom over to Weberstein. Let's try this again. There. Can you see the first picture had that same shape of exploding from the center. Right, now the vectors are a little bit longer. You can tweak it, but you just need to see the shape. If you can see the shape, if they're all quite different, you know, the vector length don't matter, right? You can basically see what the one is, and that's essentially what you would be doing in that question. Now that guy, oops, let me kick these off. They are distracting at the best of times. Up, down, okay. That's interesting. Why is it still there? Huh. So question 2 we just did. There's question 3. It looked almost exactly the same as 2. Do you see there's a minus there instead of a plus? So that will change the shape. Here's question 4. Good to go. And we are now over that little hiccup. And now we can do stuff that doesn't need me jumping about all over the place. So a vector field in 2D looks like this guy. You can put it into that software I've got, you know, whatever the equation might be, this fella, and you can imagine it getting drawn and you would pick somebody from it. And that basically gets you through questions 1 to 4. And then from 5 onwards, we are going to start with a function in 2D, this guy. And we are going to find the gradient guy. He's actually a gradient vector. And we know how to do him, because didn't we use him when we were trying to do Lagrange multipliers? So guess what? You're going to do him again. If you differentiate this with respect to x, and that's meant to say xy, not x comma y, you are going to get 4y, the cosine of xy, and since you're differentiating it with respect to x, that's like 5x, so you get another y. And if you want to differentiate it, I'm doing that again. There's the first one. If you want to differentiate this function with respect to y, you got a lot of work, because you essentially have a product rule. So that'll be your f and that'll be your g, because both of them contain a y, and so it's going to be f dash j plus f of g dashed. The derivative of this guy is 4. Leave that guy alone. That guy you leave alone. And this guy you differentiate with respect to y, and that will get you a cosine of xy times the derivative, which generates another x. So the first guy looks like that, and the second guy looks a little bit messier. 4 sine of xy plus 2xy, the cosine of xy. So really just finding gradients, isn't it? The gradient vector. So how about a gradient vector like this fella, which is a version of question 7. Suppose we want to find the gradient vector of this 3-dimensional function. Well, first thing I'm going to do is write it in a format that's going to make differentiation easier. So I write it as a half power. Now, if I want to do the partial derivative with respect to x, it's essentially a chain rule here. So you've got 4, and then you multiply by the power and reduce it by 1. And then you multiply by the derivative of the inside function with respect to x, which is that guy. And you are now looking at that, because the half and the 2 cancel off, and so x over here. And then for style points, okay. McCool, partial derivative with respect to x. Now, I do not need to do a lot of work to get the other two. Agreed? Symmetry. Have you noticed this function is symmetric? So I should be able to make a reasonable prediction on the other two. So I'm pretty sure that's going to be the bottom. All I need to figure out is what should the numerator be in each case. What do you think this one is, the middle one's going to be?
4y.
I agree. And would your other one be 4z? So you want to put this guy into WebAssign, then the gradient vector of f will be this guy, comma this guy, comma this guy. So it's going to be 4x over that ugly square root, 4y over that ugly square root, 4z over that ugly square root, and finish with those brackets. And those brackets you can find in WebAssign, right? You go into vectors, you'll see a guy that looks like this, and you can put it inside. You can also do it by doing 4x over this ugly guy I plus 4y, the ugly square root j, plus 4z, the ugly square root k. But the vector I, j, and k have to be the vector I, j, and k that you'll find in WebAssign. You can't just hit the keyboard I, keyboard j, and keyboard k, because WebAssign won't know what you're meaning, and it will tell you you are wrong. I would consider what I've just done here revision, because we all know how to find gradients, right? We're just telling you that the full title is gradient vector now. And I will do one, but only one of the last question, one piece of it. It's a 3-dimensional guy again. It's an x cubed, a y, an e to the y over z. Okay, let you pick. You want me to do x, do you want me to do a y, or do you want me to do a z? And I suggest you pick the one that you think's the hardest to do. Which one do you want me to find the partial derivative of?
How about
How
Z?
about C, yeah.
Yeah, I like the one who said, Antonio said Z. Teresa, you have got to learn to do the mathematical letters of the alphabet. It is not Z, it is Z. You got that
Z.
now? Z. Okay. This is going to start off nice and finish ugly. It's x cubed y e to the yz. That's the nice bit, right? Then you finish by differentiating what we call the inside function. Now, if you differentiate y over z with respect to z, you will get negative y over z squared. And let me try and prove that to you. Y over z is yz to the negative 1. Multiply by the power and reduce the power by 1, and then make it look pretty. Okay? Now, you don't leave things hanging like that. If it is possible, you should tidy it up, or at least combine things. There's your z. Agreed? Your partial derivative with respect to z. Now, if you wanted to do y, it would be different, right? At least a little bit of it would be different. If you wanted to do x, actually x would be the easiest, wouldn't it? Just be 3x squared, all of that guy, right? 3x squared, all that. So the x's would be the simplest. And then you plug the whole thing in and you call it good. Any questions about using the software to draw two-dimensional vector fields and then to do with gradients even? Any questions? Are we good to move on?
I'm good.
Right, let's do it. And I said half an hour, and am I good? Am I good? According to my watch, it's 28 minutes. So this is now the bread and butter one. And by that, I mean the stuff that's really going to be more used to you. Line integrals. Now, there are three different flavors of line integrals. You're going to get line integrals that have this shape, right? It's going to be some function of x and y ds, or some function over here ds, or whatever it is. So this might say x cubed plus y cubed ds. This one might say x, y, z squared ds. The key is that they have a thing called ds. Do you see that? So we're differentiating across the surface, I believe, when you see that. And you're saying, what is the surface? Whatever this thing is the surface. That's what I believe it means. Then you get line integrals that look like this. P dx plus q dy, or PQR, kind of 3D version. This is a two-dimensional line integral. This is a three-dimensional line integral. This is a two-dimensional line integral because it only contains x's and y's. This is a three-dimensional because it contains x, y, and z. The guys that I'm calling P and Q here are themselves functions of x and y. So this guy here could be x squared y dx plus y cubed e to the x dy, right? So P and Q and R are functions of x, y, or x, y, z. And so these are just convenient placeholders. And I like using P's and Q's because there's enough F's and G's going around to confuse me anyway. And then we have this line integral, which is actually the one that I can tell you what it's calculating. This kind of line integral that is written as this: f is a vector field, dot product symbol, dr, where r is a position vector of the space curve. Right? This thing here is called a line integral. And what this does is, let's do a 2D version of what it might look like. Can you imagine we've got a vector field that looks, it takes forever to draw these darn things, but it looks like this. And you have a curve C, right? And this is be a 2D curve, and it kind of starts here, which might be t equals a, and it does a journey, and it finishes up here when t equals b, right? So can you imagine the old space curves from Calc 3, right? That's what we have here. So this guy is the space curve R of t, and we're traveling along on this orientation. At any given point in that curve, won't there be a vector associated with it? Some of the vectors will be pushing it backwards. Some of the vectors will pushing it onwards. So can you imagine a boat taking a rather circuitous route on the surface of a river? What you are calculating with this guy is the work done in getting from here to here. Right. So can you imagine all the vectors were going this way, pushing against me? That work done would be a lot, right? Now, occasionally, I might get some help because the vectors are behind me, giving me a little shove, right? So I won't be doing any work there, right? In fact, I might be picking up some speed, and that's good. In the other direction, they are working against me. So that is what this guy does. let's go back to the first kind. And I'm going to take a few moments to load this guy up if I can. Give me a few seconds to get in and out and find the guy. Perfect. Okay. So this is what question 1 looks like. Find this line integral. Oh, I better show you my guy. Right. Find this line integral. The surface would be x over z. Can you imagine z equals x over y? And we're doing a line integral over a surface, ds. This curve, right, is described by parametric equations involving t. And the curve starts at t equals 1 and it finishes at t equals 2. So you always describe the curve C in form of parametric, right, in terms of t. You could have described it and it would be equally correct by doing it using this notation. Can you remember the space curves way back in Calc 3, right? This guy is exactly the equivalent information to that guy. Basically, that's who x is and that's who y is, right? So that's what we've got. So we are going to take this function and we're going to use this curve from t equals 1 to t equals 2. And, well, there is a formula that you use for guys that look like this. So let me give you the formula. Essentially, everything turns into t's. So it's going to be the integral from t equals a to t equals b. You don't have x anymore. X gets replaced by this guy. You don't have y anymore. Y gets replaced by this guy. Right? So essentially, the function gets replaced by equivalent t's times square root of dx by dt squared plus dy by dt squared dt. That guy is going to be essentially what ds is. So this guy is ds. And this guy is x over y. Have you noticed that everything now is a t, even if you can't see them all, they are all t's. So let's continue. T cubed over t just gets me 1 over t. Square root of, if you differentiate this guy, you get 3t squared and then you square it. Plus, if you differentiate this other guy, you get 4t cubed and then you square it dt. Can you see the integral is now nothing but an integral, a Calc 2 integral really, in terms of t. And the rest of the work that we're going to have to do here, I better put 1 and 2 in because that's a and b, is to make this pretty style points so that hopefully it turns into something we can integrate. That guy squared is 9t to the 4. That guy squared is 16t to the 6 dt. You all comfortable about that? Okay. Now, that t looks kind of weird. Let's make the t a little bit more obvious. Tell me what I can do to make that square root more helpful. Algebraically, how could I rewrite that square root to help? Any ideas?
You can write it with that 1/2, or you can
Do
factor
something
out-
before that. Yeah.
Factor out a t squared, right?
What's the biggest amount you can get out? That's a 6, by the way.
Oh, that's a 6?
So you could do a bit more than t squared, right?
Yeah,
Take the 4.
right.
Then that guy, and I'm putting more lines in than maybe you would choose to if you were doing it, but that's fine. It now becomes that guy. So it's going to be the integral from 1 to 2, 1 over t. That guy is t squared, and this guy is 19 plus 16 t squared dt. And finally, the best we can do with style points is that guy. Right, so I want you to think Calc 2 here, Calc 2 integrals. I want to integrate this function. What technique am I going to use?
Use substitution.
Great. Who would the u sub be?
9 plus 16t squared.
Agree? Don't you always pick the ugly guy inside the square root as well? Not always, but majority of the time. So now I can differentiate with respect to t. Then I can do the crossover. Then I can divide both sides by 32t to isolate the dt. So I now have an integral t square root of u times 1 over 32t du. The t's cancel, and I have 1 over 32. The square root of u, like John was saying, now we'll use it, becomes u to the half du. Power rule, add 1 to the power. Dividing by 3/2 is like multiplying by 2/3, and that gets me a 48th. That then becomes this guy, who in turn becomes that guy. And at this point, we then can plug in the t equals 1, t equals 2 guy. And you're going to trust me because it's downright ugly. But you end up with, I'm just looking at their answer, you end up looking like that. And oops. You're going to get some ugly square roots that simplify 73, root 73, and the other one actually comes out really nice, comes out as 125. So that's kind of cool. And that is our first line integral where there's a ds involved. So it's not a short question. You agree there's a lot of stuff to do. There is turning everybody into t's. And then depending on what you've got, maybe you'll get lucky and this will be nice, but the chances are it won't be. And don't you have to do a lot of work to get it to look pretty, style points? And then once you got it pretty, it's probably going to be a u sub, an integration by parts, maybe. And it might be one of those weird standard integrals. You know, if it ends up the answer's just that guy, can't you look at the back of the book and find out who he is? Right. So that's your most likely scenarios for this type of question. Okay, and that's actually virtually question 1. There wasn't really that much between what I did and what you're going to do. Now, every question virtually has its own little thing going on. So here is another line integral. Oops, I misread that. That's a 4. There it is. And C is the circle. And it's a circle x squared plus y squared equals 4. And it's going counter clockwise. So this one has an added thing that we didn't have in question 1. And that is, I do not have the parametric equation for a circle, radius 2, going counterclockwise. I can draw it. Right, would you agree it's going that way? And I know it's radius. But what I don't know yet is how to rewrite it in terms of t as a parametric. But there is a way to do it. Agree? In a way, isn't it like a hidden polar? That's the guy. So, in this integral, oh, by the way, if you're going to do an entire circle, wouldn't you have to go from 0 to 2 pi? Because it's an incomplete circle. So I'm going to do an integral from 0 to 2 pi. Check. The x is going to be 2 cosine t's. The y's are going to be 2 sine t's to the power of 4. And the ds is going to be that guy again. Take it a little bit further. You get a 2 cosine t, 2, 4, 8, 16 sine to the 4t. If you differentiate this guy, you get negative 2 sine t and then you square it. And you do the other one, you get 2 cosine t's and then you square it, dt. 2 and 30, that gets me 32. That gets me a cosine t. I have a sine to the 4t. And now I'm going to cut some corners. That guy will be 4 sine squared plus 4 cos squared. Do you recognize 4 sine squared plus 4 cos squared? What's it equal to? 4 sine squared plus 4 cos squared. What's that thing equal to? That's right, John. 4. So that's basically just times another 4. 4 times that guy is 128. I'd probably pull it out because it's getting awkward. And that's where I'm stopping. You tell me what u sub you should use for this integral here, because there's one u sub that is easy and one u sub that doesn't work.
The 4 doesn't become a 2.
No, the 4 is from this bit here. So it's still 4 all the way. So I'm not sure. So what u sub would we use in this integral? Your choices are sine t or cosine t. Thomas, you get any ideas? Sine t, cosine t, which one would you go for? 50-50? Let's see what you say. And Thomas says, well, choose sine t. If you choose sine t, you will end up with u to the 4. If you choose cosine t, you'll only eat up one of these. You'll have a u here, and then you'll be left with sine cubed t, and sine cubed t is bad news. So the u sub that you should have chosen here was sine t. Now, it's not an end of the day, because see if you pick the wrong u sub, about 2 lines into the working, aren't you going to know it's the wrong u sub? Right? You're going to have bits you know, you're going to have a sine cube t or a sine t left over, and you know that you can't get rid of it, and that's a good sign that you've picked the wrong one. Any questions about that one before we move on? Okay. This is my version of question 3. A line curve. X squared plus y squared plus z squared. ds. The curve C, thankfully, two t. Y is the cosine of 4t. Z is the sine of 4t. And we're doing it from 0 to 2 pi. Okay, now the difference between this guy and the ones we've been doing is, you notice this is now 3-dimensional, right? There are 3 variables. So we're going to go t equals 0 to 2 pi. X squared becomes this guy squared. Y squared becomes this guy squared. And z squared becomes this guy squared. Times the square root. And we expand this square root formula to now be dx by dt squared plus dy by dt squared plus dz by dt squared. Obviously, integrate with the dt. So it's 0 to 2 pi. 4t squared, cos squared 4t, sine squared 4t. Check. Differentiate 2t, you get 2 and square it. Differentiate that guy, you will get -4 sine of 4t, and then you square it. Do that guy, and you'll get 4 cosine of 4t, and then you'll square it, and everybody finishes the dt. It might not look the usual way for this to look, but nonetheless, that thing simplifies. Sine squared 4t plus sine cos squared 4t plus sine squared 4t is equal to a number, and it's equal to the number 1. Sine squared x plus cos squared x is 1. Sine squared 1,000,000 t plus cos squared 1,000,000 t is 1. As long as these are the same number, the cos squared of it plus the sine squared of it will always be 1. So the connection sine squared x plus cos squared x equals 1 is just one member of the whole infinite family of that relationship. Times square root of 2 squared is 4. That guy is 16 sine squared 4t. That guy is 16 cos squared 4t dt. So let's integral from 0 to 2 pi. 4t squared plus 1. Bit of a silly question, but I'll ask it anyway. What do they two guys get you when you combine them?
16.
16. So that basically is what, the square root of 20? Okay, I would pull out the square root of 20 and just integrate this guy. In fact, I wouldn't leave it as the square root of 20 because it can be written as 2 root 5, which is nicer. And power rule, and off you go. So over these last two questions, if you look at what knowledge we expected you to know, you had to know that a circle can be written down in the parametric form like this. You had to know some trig identities, like this guy gave me this. You had to combine them. In the previous question, didn't we also have to remember that u-subs can be used to find integrals? So a lot of different pieces that you would have picked up from, oh, I don't know, from Calc 2 onwards, Calc 1, if you think of some of the differentiation, is, you know, it's knowledge that you just expected to know. We're now looking at line integrals of this format. So P dx plus Q dy. And that's just a 3D version of this. Now, C is a curve in 3D. And you would normally expect it to be written down like x equals, you know, some function of t, y equals some function of t, right? So it might be t squared and, you know, sine t. And how do we convert it? Oh, and you're going to have a t from a to b. So C is some curve written down in parametric form, starting at t equals a, finishing at t equals b. And this is what it would look like. It would be the integral from a to b. P is a function of x and y. And so is Q a function of x and y. So you're going to have P times dx. Right. If you are given x squared as that, then you can differentiate with respect to t and get that. And you can then do a crossover. And what you now have is a differential that says dx can be written as 2t dt. And 2y would be that one. You'd get cosine t dt. And p and q, well, whatever the x's and y's are, they would also get turned into t's. Now, as you can probably see, it's quite difficult to generalize what that formula looks like because there's so many moving parts, right? The curve has to be parametric, P has to have x's and y's in it, Q has to have x's and y's. You can't really write it down in a clean format. So I'm not going to try. That was my best attempt. What you're going to be able to do is, when they put some meat on the thing, actually give you a question that you can kind of work with, then it becomes something more practical. So let's take, for example, I want an integral of x squared dx plus xy dy. There's a line integral. Let's tell you the curve C is given by the parametric equation t squared plus 1 and y by the parametric equation t cubed. And let's say that t is going to go from 0 to 1. So that's all part of what you know. So basically that guy I call P and this is the guy I'm calling Q. But now we've got some things, you know, around that being general. So how do you go about the whole process? Well, the integral goes from 0 to 1. X squared becomes this guy squared, dx, plus xy becomes this guy times this guy. So that's t squared plus 1 t cubed dy. Are we comfortable so far? Right. The x comes from the curve. The y also comes from the curve. Now,
You gotta square the t squared plus 1. Right?
well done. Yes. Now, to find what dx is, take this guy differentiate them with respect to t, and you get 2t. Do what I call the crossover, and now you know who he is. So it becomes the integral from 0 to 1 of t squared plus 1 times 2t dt plus t squared plus 1 t cubed. Now, if you want to find what dy is, start with the curve, right? Y equals t cubed. Differentiate it with respect to t, 3t squared. Do the crossover. And now you have times 3t squared dt. And I'm just going to take this guy a little bit further. If you multiply this out, you get 2t cubed plus 2t dt. And this guy gets you 3t to the 5. So what's that going to get me? 3t to the 5, 3t to the 7 plus 3t to the 5 dt. And now I can put the whole package together. Now, in this particular example, did you notice none of the terms could add and subtract? But can you imagine in another world, there might be some guys here that combine with these and you simplify it down. That's the integral for this guy. We cool? Pretty much this is the guy that does everything, isn't it? X gets replaced by him, Y gets replaced by him, a little bit of work, dx gets replaced by him, a little bit more work, dy gets replaced by him. When you're finished, there's nothing but t's. And this is a Calc 2 integral that you can do with the power rule. Any questions? Oh, I have a chat, so that might be a question. Oh, yes, you're right, Thomas. Any questions? Okay. Suppose I gave you this integral. And the curve C was described as x equals, I don't know, t squared, and y was e to the t. And t goes from, because I have no imagination, 0 to 1, right? And this line integral looks almost like Calc 2, but it's not. Technically speaking, this is what we've got. Do you see the dx part isn't there because there's 0 of it? So it's not a Calc 2. You don't just say, oh yeah, integrate by y, a half y squared, my answer's a half y squared, x squared, plug in that guy, and go for it. That would not work. The fact that the dx or the dy, whatever it might be, is missing is not a big issue. So back to the original, t is going to go from 0 to 1. X squared is going to be that guy squared. Y is going to be e to the t. And let's get, the only guy I care about is dy. Right, I could find dx, but I'm not going to use it, right? Because it would just disappear here again. So I'm only going to do the dy piece. And dy by dt is e to the t. So dy is e to the t dt. And so we now have the integral from 0 to 1, t to the 4. Those two guys don't get e to the 2 t squared, they get you e to the 2t, and we're looking at that guy. And that's where I'm going to stop with this one. You tell me what technique from Calc 2 you use for this fella.
I think you'd use integration by parts.
You would. And it depends on who you were taught by. If you're taught by me, this guy's called f of t, and this guy here is called g of t. But you might do the UDV method, and that's fine. You'll get the same answer. Of course, I'm glad I'm stopping here, because that one would actually be an integration by parts. I think you'd need to do 4 levels before you finally got your answer. So I'm glad we don't need to do that, but it is doable. Now, this is a version of question 4. And we're doing a line integral of the curve C. I wonder why, I just thought, because my brain's like this, why it's called a line integral. Shouldn't it really be called a curved integral? Because C is almost always a curve anyway. But, you know, that's semantics. So it's an x, y, e to the power of yz. And the only good news is it's a dy version. So it's not got a dx and a dy, right? Now, do you notice it's got 3 variables here? X, y, and z. Technically speaking, this is 0 dx, that guy dy, and 0 dz, because all line integrals have all the components. It might be that some of the components are zeros and therefore you don't need them, right? But they're still there. You know, it's a bit like 1x, the 1 is still there even if you don't write it, right? Now, we are given a curve, C, and it's 3t, at least in the one I'm looking at. This guy is 4t squared, and z is equal to 3t cubed, and WebAssign has no imagination either because it is 0 to 1. So my integral is going to be from t equals 0 to 1. The x is going to be 3t times the y, which is going to be 4t squared, e to the power of y, which is what, 4t squared, times a z, which is 3t cubed, finally with a dy. So let me just tidy this up first before I do the next line. So that's 12t cubed e to the 12t to the 5 dy. Are you good with that? Now, since there's only a dy term here, I only need to use that guy to get dy. So dy by dt is 8t. So dy is going to be 8t dt. I guess in a way, isn't this question transforming x, y's, and z's into t's? So it's like a substitution method, right? It's different than the substitution we did on Monday, but it's converting from one variable or combination of variables to another, in this case, t's. So it's going to be the integral from 0 to 1, that guy, times an 8t dt. Right, 8 times that guy gets me 96, and I'm pulling them out. And now I have a t to the 4, 12t to the 5 dt. And that's where we are right now. That's where I'm going to stop, right there. Pretty much the same kind of question I'm going to ask a lot of times for what's left of today. Tell me what technique I should use to integrate this fellow.
Use substitution.
Agreed. And wouldn't the substitution be 12t to the 5? There's a lot of Calc 2 stuff appearing today, isn't there? And a little bit of Calc 3 with space curves, which that's essentially who this guy is. Question 5 is very similar to the one I've done. Let's do question 6. we've got this guy, and it's a z squared dx, an x squared dy, and a y squared dz. So it's a line integral with all three variables now, right? Instead of just one of the three. And the curve C is actually a line, and it's a line joining the point 1, 0, 0 to the point 3, 1, 4. And we have to find the parametric equation of the line that joins 1, 0, 0 to 3, 1, 4. Now, when you did this type of question in Calc 3, right, been a while since you've done that, so let me remind you how we would do it. Can we pretend that that's the point P, and I'll call it 1, 0, 0, and up here is the point Q, and it's going to be called 3, 1, 4. The first thing you do to find the equation of a line is you find what's called its direction vector. In this case, PQ. Great. And the way I remember it is second guy take away first. So 3 take away 1 gets me 2. 1 take away 0 gets me 1. 4 take away 0 gets me 4. Does that ring any bells? Once you've got that, that's heart of it. You choose a point, and I'm going to choose the first point because I want to make sure my direction that I'm traveling is this way. I'm going to go that way, right? So I'm picking that as my point. Okay. So this guy and this guy can now be used to get your equation. 1, 0, 0. 2 gets me 2t. 1 gets me 1t. And 4 gets me 4t. So that guy, and that guy. There's the parametric equation of that line. So far, so good? So over here, 1 plus 2t. Over here is t. Over here is 4t. So here's a new skill set that we haven't used for ages. How to find the equation of a line joining 2 points in 3D space. There it's parametric equation. Not finished. I need a start and a finish t. Okay, so I'm going to start here. I'm going to finish here. And I need to know what value of t gets you this point and what value of t gets you that point. So let's suppose I wanted this guy. Looking at this equation here, would you agree t equals 0 gets you the guy? So that's the easy one, because it's always going to be t equals 0. What's going to be a bit harder is to find out who that guy is, right? You see it goes 3, 1, 4. Anybody want to have a guess at, or tell me if they know how to find it, what the t value you would need to generate the point 3, 1, 4 using this equation? And it's something you could probably do in your head if you think about it. What value of t plugging in here would generate
So
3, 1,
1.
4? It's be 1. And here's the good news. If you ever get another question where it's taking one point to the other, as it is here, the start number is always going to be 0, and the finish number is always going to be 1. And it's kind of because of the way the equation was created that you're doing one movement from 0 to 1, right? One direction. So we got it. And now we have everything that we need. So it's going to be the integral from 0 to 1. Well, I just thought of some. See, if you never know the answer, wouldn't you do t goes from 0 to 1 because Weber sign has no imagination either? I mean, it's a guess, but wouldn't it work an awful lot of times? Z squared, 4t squared dx x squared, 1 plus 2t squared dy, and y squared is t squared dz. So it's going to be an integral from 0 to 1, 16t squared. Right, if this is x, then dx by dt equals 2, and dx is equal to 2 dt. So I'm just going to do times 2 dt. If I did the next guy, dy is going to end up being 1 dt. And if I do the last one, dz is going to be 4 dt. Are you comfortable with that? Okay, I guess I'll do maybe one line more. 32t squared, 1 plus 4t plus 4t squared, and then another 4t squared dt's. And I'll stop here. Wouldn't you combine like terms to get one integral with a dt and use the power rule? And that would be the end of that one. So are we comfortable about line integrals that have this form? Essentially, everything is turned into t's, right? The x's, the dx's, the y's, the dy's, the z's, the dz's, whatever you've got, all get turned into t's. And then you basically have a Calc 2 integral. Cool. Right. One last one of this type, because it's weird. You get a guy that looks like this, and it goes from the origin to this point here with coordinates 5, 1. And then it goes down here and it ends up at 6, 0. So it goes like this. And the function that we're going to find a line integral for is x plus 5y dx plus x squared dy. What makes this weird is that it isn't actually one straight line, it's actually 2 straight lines. So what you have to do in this question is break it up into 2 distinct integrals. And I'm going to call this line C1 and this line is C2. Now, technically speaking, see if this zigzagged up here and did a third line, wouldn't I break it into 3 pieces? The line integral on the line C1, the line integral on the line C2, and the line integral on sine 3 and 5 and 25 and keep going. But thankfully, we only have 2. So that's a good start, but there's still some work to do. Let's focus on just one of those. Let's look at C1. Right. Now, it's 2-dimensional. And we need to turn that into a parametric equation. Right? And if I just said to you, find the equation of the line joining, let's call this guy P, to this line here, let's call that guy Q. You can do that. You would find the slope. That guy take away that guy take away that guy. You would get a slope of 1/5. You could then use this equation here, and you could come up with 1/5 x. And now that I'm thinking about it, couldn't you probably wrote the answer right off the bat just by looking at the fact it passes through the origin and that its slope is 1/5? Well, unfortunately, that guy is no good because that guy isn't parametric. Parametric has to have X and Y written down in terms of T. It doesn't mean that we don't calculate that guy. It just means that we use it to get this guy. And here's a lovely little trick. There is the parametric equation. You make X equal to T. If X is equal to T and Y is 1/5 X, won't Y be 1/5 T? So turning a straight line in 2D or a curve or anything, it's simply just make the X T and the Y can be whatever the formula is. Now I still need to know a start value and a finish value for this guy. Well, if you start at 0, 0, won't X be 0? If you end up at 5, 1, what will be the T value that will get you to 5, 1? And it's not 1. What value of T would you need to do to plug into here to get to the point 5, 1? Correct, 5. We comfortable with that? Now, it's not like the 3D one. In the 3D one, it's a lot easier. Isn't the first guy T0 and the end T1, right? Because the way you created it, that's just going to happen. These ones are not so clean, right? So this equation here is going to be from T equals 0 to 5. X is going to be T. 5y is going to be 5 times 1/5 T. So that's that stuff. And dx, oh, I could do this without the working. Won't dx just be 1 times dt? And now the second piece is x squared, which is that guy squared. And I can do dy without a lot of work. Isn't dy going to be 1/5 dt? So let's just focus on this integral and worry about that one here later. A little bit of tidying up to do, but not much. I've got integral from 0 to 1 of 5. Well, that's t, that's a t. And this guy here is 1/5 t squared dt. And that becomes the integral from 0 to 5 of 2t plus 1/5 t squared dt. And can we just get the answer to that the usual way? Okay, let's move on. So that's me doing C1. Let's move on to C2. And we've got a point Q, which is 5, 1. And let's call that guy R then. And R is 6, 0. And I want to go that way. So it's important that I realize he's first and he's second. And this time I think it is going to take a little bit more work. 0 take away 1, 6 take away 5. Oh, prove me wrong. Slope's -1. I could probably have counted boxes on that. Y take away y1 is m brackets x take away x1. Use this guy as my starting point. Y take away 1 is -1, x take away 5. Y take away 1 is negative plus 5. Add 1 to both sides. That's the equation of the second line C2. No use to me, but it will generate this guy. Make x equal t, then won't y just be -t add 4? Do you see the little trick? Now, I need to have a start t, and I need to have a finish t. Agreed? So I need to figure out what value of t do I need to start at 5 or to end up at 5, 1, right? So what value of t? Well, x is t, since that's 5. Would you agree that's 5? What value of t will I need to finish up at 6, 0? Hopefully. Did I get that right? Let me check that. Negative 1, 1. Okay. Negative 1 here. Negative x. Okay. Negative 5. Add 1. Okay. So where would I need to go now to get to the second guy? And nobody noticed. Oh, I did. I noticed. I'm cool. Oh, take it back. I didn't. I wasn't getting the numbers I was hoping for. So let me just redo the guy. And I'm physically going to write them down. Okay. So why is that guy not giving me 5, 1?
Should be negative x plus 6.
Is that what it should have been? Yes. Thank you. Okay, now I'm happy. Negative x add 6, t and negative t add 6. Okay, if you want to get this guy here, right, make t 5. And you'll get 5, 1. Now is good. To get this point here, right, won't you make t equals 6? Ah, perfect, it's a match. Right, t equals 5 to t equals 6. Have you noticed that it's just the x coordinate as the start and finish? And I couldn't figure out why it wasn't working. It was because of this guy. Add 1 to both sides, you get 6. Right. Whew. Okay, so I now have everything that we need. The x is t, the y is negative t add 6, and we're going to be starting at t equals 5 and finishing at t equals 6. So this integral here would be from 5 to 6. Instead of x, I'm going to have t. And instead of 5y, I'm going to have 5 negative t add 6. Then I'd have, instead of a dx, I'm just going to have a 1 dt. Instead of x squared, I'm going to have t squared. And instead of a dy, I'm going to have a negative 1 dt. So this is going to be the integral from 5 to 6 of t, take away 5t plus 30 minus t squared dt. So that's going to be the integral from 5 to 6 of negative 4t plus 30 take away t squared dt. And we're done. Well, apart from my little hiccup of not knowing to add 1 to both sides to get the right equation of the straight line, if it caught that, it would have been a lot smoother looking. But essentially, break it into 2 pieces and do, you know, the same similar thing. Find equation of the line and convert it to parametric. Find equation of line C2, convert it to parametric, and you end up with quite different looking, actually, integrals as well. How are we doing? We cool? Okay. Last type. We have a number of questions, starting at number 9 and finishing at 11, so only 3 of them. We're doing good time as well, which is nice. We are going to be asked to find the work done. And the work done can be found by calculating a line integral of the dot product of the vector field f with this thing called dr. So let me tell you how you get dr. dr is essentially just r dashed t dt. The curve C is going to be described by a space curve. So it might be described like this: t squared 2t e to the t. If that is your space curve, then r dashed of t will be 2t 2 e to the t dt. Your vector field F will be a P, a Q, and an R, where P, Q, and R are functions of X, Y, and Z. And the X's get replaced by him, the Y's are going to get replaced by him, and the Z's are going to get replaced by him. So again, a bit like the last one, it's very difficult to generalize this. There's just too much going on. But if I try my best, it might look something like this: P, Q, R, dot product, R dash T, dt. And if you think about this guy here, X, Y, Z, basically you're going to have a derivative times this, plus that, plus that. In a lot of ways, it'll look like this guy. Okay, let's try and put some meat on that to show you what it kind of really looks like. And what's the first one like? Okay. Find the line integral f dr. The vector field f is given as sine x, cosine y, xz. The space curve, that's C, is described by t to the 4 minus t cubed t. And guess what? T goes from 0 to 1. So we're going to find this line integral of this vector field with this space curve traveling through it. So imagine you went to the vector field and saw those little 3D arrows pointing everywhere. Can you imagine a curve going through it? And you're trying to essentially find the amount of work that it would take for this space curve to pass through this vector field from t equals 0 to 1. So let's get all the different components and then we'll put them together. F is equal to sine x, cosine y, xz. X is going to get replaced by this guy. So it's the sine of t to the 4. Cosine of y is going to get replaced by this guy. So it's going to be the cosine of t cubed. And xz is going to be replaced by x times this guy. So that guy times that guy, I believe, is t to the 5. And now we have the space curve in terms of t. Sorry, the vector field in terms of t. Now we'll take r of t, the space curve. Let me check that. Yes, that's a negative, by the way. And t going from 0 to 1. Its derivative is 4t cubed, take away 3t squared, double check, times 1. This is the version of f that we're going to use. This is the version of r dash t that we're going to use. So when we put them together, this line integral becomes the integral from 0 to 1. The vector f, which is that guy, that guy, that guy, dot r dashed of t, which is this guy, 1, dt. Now that is a dot product, a 3-dimensional vector dot product with another 3-dimensional vector. So what you're going to get is the integral from 0 to 1, this guy times him, So that's 4t cubed, the sine of t to the 4, plus that guy times that guy, so I guess it's a negative, 3t squared, the cosine of that fella, plus that times that, which is t to the 5, dt. Right, now we have the last piece of the puzzle, which is how do you integrate something like this? And the answer, I think, would be, at least in this question, would be to split it into 3 different questions. What technique will I use to integrate 4t cubed sine t to the 4?
U sub.
And t to the 4 would be our guy. What would I use to integrate negative 3t squared cosine of negative t cubed?
Same.
Just a different u sub, right? Which is probably why it's a good idea to separate it in 3 integrals. And isn't that last guy just a power rule? So, dot, 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 dot. So the trick to doing these is convert the vector field into t's using the space curves x, y, and z components. Find the derivative of the space curve, boom, boom, boom. Do a dot product of them, and if you do it right, you'll just have a single integral with t's. And the integral, if you're lucky, you can do in one go, but if you have to break it into pieces because they're a little bit trickier, then that's what you do. Are you okay with that guy? No questions?
It just seems like a lot of work.
It is. I wish I could tell you that the next few weeks the questions are going to get shorter, even if they are going to get harder, but that's probably not true. The higher up the food chain you get, the questions do take longer. I'll share some with you. I still remember way back in the day when I was at university, doing one question from start to finish, not really making too many mistakes that would slow me down, taking over an hour. That's kind of what happens the further up the food chain you get. There's like a level upon a level upon a level, right? You have to do this, and then that becomes this, and then so on and so forth. And yep, it's goes with the territory. Here is the guy that's our space, is our vector field. He's okay. And we are trying to find the work done in moving from the point 0, 0, 1 to the point 3, 1, 0. And I'm calling them P and Q. So can you see in this question, you have one more level. Isn't the first level to find the parametric equation of this line? And then once we do that, then we can start doing this stuff, right? Okay, well, imagine this is P. Here it is. Imagine this is Q. We've done one of these before today. We get the direction vector, PQ, and 3 take away 0, 1 take away 0, 0 take away 1. Who's that guy? We choose as our point this fella. And now we can get the equation. And I'm not going to write it as we did the last time as parametric. I'm going to write it as a space curve. So 0 plus 3t, 0 plus 1t, 1 minus 1t. And so our space curve is a 3t, a 1t, and a 1 take away t. Are you happy about how we got the equation of the line from P to Q? Now, at the same time, before I forget, don't we need a start and a finish? A value of t that gets you the first point and a value of t that gets you the endpoint. But for a line in 3D, isn't the answer going to be from 0 to 1? That means we actually have everything that we need. Let's start with f again. X minus y squared. Now, you could definitely cut out some lines here. I mean, if you feel comfortable about it, you know, I'm repeating a lot of things because these are notes, but you might be able to say, well, I don't need to write this again. I can see it up there. I'll use it. X is what? Got a little reminder. X, Y, and Z. X is 3t. Take away t squared. Y is what? T. Take away that guy squared. And this guy is 1 minus t. Take away that guy squared. So it's going to be 3t take away t squared. Oh God, if you FOIL that guy out, you're going to get 1 minus 2t plus a t squared, then you subtract everybody. So you're going to get a t squared. You're going to get a minus t. You're going to get a minus 1. Hopefully that's right. And this guy is going to get me 1 take away t, take away 9t squared. And now I'm happy. I have my vector field in terms of t. Now I already know who r of t is, so I'm just going to write down his derivative. 3, 1, negative 1. And that's the other guy I need. So to get the work done in a line from this point to that point, passing through this vector field, the work done is the integral from t equals 0 to 1, the dot product of f with r dashed of t dt. It's the integral from 0 to 1 of all this stuff. Dot product with 3, 1, negative 1 dt. That's probably as far as I'm going to go now. 3 times this guy plus one of these guys minus one of these guys. Okay, wouldn't you just FOIL this out, collect like terms, and you have an integral with t squareds and stuff? And that would be the end of that question. Are we good? But a lot in it, I guess. And that is perfect timing. I didn't realize it. It's the last question.